Hello everyone, my name is Salman Bawa, and today the topic of my presentation is at the junction. We will begin by exploring how a junction forms and what are the types of junctions. We will then look at the charge, the field, and the potential at the junction, and have a look at the band diagram of a PN junction in a simple Excel graphical calculator. We will then cover the complexities and considerations that we need to make when we are dealing with heterojunctions and the summary of the presentation. So why are junctions so important? Well, without the junction, we would not have diodes and our transistors, LEDs, and we would not even have solar cells without junctions, whether those be crystalline solar cells, thin film solar cells, or multi-junction solar cells. So the formation of a junction leads to the several products listed here on this slide. So how does a junction form in a semiconductor? Well, it forms because of a change. That change could be abrupt, steep, or gradual. The change is in either the doping of the semiconductor or the material of the semiconductor. So let us look at doping. We could dope the semiconductor p-type on one side and n-type on the other side, which means that the carrier concentrations would be different on each side of the semiconductor. So as the carriers flow at the center of the semiconductor, we would have a region where the carriers cross over. And when that happens, it leads to fixed ions, and it is depleted of the mobile carriers. This depletion region forms the width of the junction. And obviously it would be P side on one side of the junction and N side on the other side of the junction. And because of these fixed ions, we have a charge density developed at the junction that causes the electric field, that causes the potential, and hence the energy band diagrams. Another way of forming the junction is to use a different material, which means that two different materials, completely different materials, could join together. And when that happens, we have to consider the intrinsic carrier concentrations of the two different materials. The electron affinities of these materials with respect to the vacuum level. The width of the junction would depend on the type of the material that we are using, and the relative permittivity of that material would play a role in the width of the junction. So the width in material 1 could be very different from the width of the junction in the material 2. But because of this difference in material, and at the junction, we have fixed ions formed. So there'll be a charge density. There'll be an electric field, which would cause potential, and then the energy band diagrams. A junction has many names. It's called a junction. It's also called a depletion region, space charge region, and in case of solar cells, we hear the word tandem solar cells. But there are two types of junction. One is a homojunction. As the name suggests, this is the same material, and so the only way to form a homojunction is via doping. And the doping could be different on each side, an N-type and a P-type, and so we'll form a junction. The other way to form a junction on another type of junction is heterojunction. In case of heterojunction, the materials are different, and these are formed using epitaxial growth methods. So one material could grow on top of another material to form the junction. So what are the contents of a junction? If we explore carefully, once we form a p-n junction, the mobile carriers would travel close to the junction, cross over, and form fixed ions. These fixed ions form on the p side and the n side. And this is the formation of the junction. There's a density of negative charges on the p side and a density of positive charges on the n side. And these charge densities form an electric field that results in a potential or a built-in voltage. And all this leads to the very important energy band diagram. This band diagram shows the energy levels of the valence band and the conduction band and the Fermi level in the p-n junction. And we know that it is because of this that we have a built-in voltage, and so we need a certain voltage that has to be applied to the p-n junction to forward bias. And when we forward bias, the QV0 that you see on the slide decreases. And if we reverse bias, the QV0 on the slide increases, making it difficult for the carriers to move in the junction or across the junction. So the energy diagram is very important in understanding the function and the operation of a junction. In fact, Herbert Kromer said that if in discussing a semiconductor problem, you cannot draw an energy band diagram, this shows that you don't know what you're talking about. If you can draw one, but you don't, then your audience won't know what you're talking about. So the energy band diagram is extremely important. So let us explore the role played by each of the contents of a junction. When we dope a semiconductor p-type on one side and n-type on the other side, there is a carrier concentration gradient that forms. And because of this, the carriers diffuse towards each other. At the point where they meet, they cross over and recombine. Once that happens, the region where the recombination occurs is left with fixed ions. These are positive donor ions, N sub D on the N side, and negative acceptor ions, N sub A on the P side. And so there is a charge concentration represented by rho of x, which is equal to Q, which is the charge, 1.6 times 10 power minus 19 times N sub D, coulombs per centimeter cube on the N side, and the charge density is minus Q N sub A, coulombs per centimeter cube on the P side. These charges cause an electric field, which is the integral of the charges or the charge density divided by the relative permittivity of the semiconductor in volts per centimeter. The integral of the electric field provides us the potential, and Q, which is the charge, 1.6 times 10 power minus 19 times the voltage, provides us the energy. We could express this energy in electron volts. Let us look at these contents of a junction in a bit more detail. So rho of x, which is the charge density, equals Qn sub d minus Qn sub a. This is assuming that the n side is on the left and the p side is on the right of the junction. And the integral of the charge density divided by the permittivity of the semiconductor is the electric field. So once we put the expression of rho of x, we get the electric field equals 1 divided by the permittivity of the semiconductor times the integral of Qn sub d minus the integral of Qn sub a. We are assuming that this junction is abrupt, which means that at x equals 0, that's where on the left of x equals 0 is the n side, on the right is the p side. Now we'll have to put the limits on the integral, and these limits would represent the width of the junction. And since n-type is on the left side and p-type is on the right side of the junction, which is at x equals 0, our integral limits turn out to be from minus x sub n to 0, which is to the junction, for q times n sub d. And the limits are from 0, which is at the junction, to xp, which is the width of the depletion region on the p side, for q times n sub a. And we know that there will be no n sub a on the n side, and there would be no n sub d on the p side. So after we integrate and apply the limits, we get the second last expression on this slide, which is 1 divided by the permittivity of the semiconductor times q n sub d x sub n minus q n sub a x sub p. And if we want to express this expression in terms of x, which is at any point of the junction, we get the last expression on this slide. So the electric field at any point in the depletion region, which is x, equals 1 divided by the permittivity of the semiconductor times this expression, the last expression on this slide. Okay, so the integral of the electric field, which is the first expression on this slide, is the potential. And the expression of the potential that you see on this slide, which is V of x, is in fact the built-in potential, or V naught. And V naught times Q equals the energy, E of x, which is the last expression on this slide. So the junction, or the depletion region, has a width W sub j, and this runs from minus x sub n on the left side to x sub p on the right side. So the width of the junction is given by the expression x sub p plus x sub n, which is equal to the expression of the W naught on this side. And the width of the depletion region on the p side, x sub p, is given by the expression that you see on this slide, and the width of the depletion region on the n side, x sub n, is given by the expression that you see on this slide. Okay, so we have gone over a number of expressions in the previous slides, and we want to use those expressions in a simple Excel graphical calculator that empowers the user to choose the left side and the right side of a p-n junction as either n-type or p-type, put in some values for the doping concentrations on each side, n sub A and n sub D, that would lead to the charges, and then the electric field and the potential, and this would all be reflected in the energy band diagram. At the same time, we want to empower the user to choose the material characteristics such as the intrinsic carrier concentration, the density of states at the conduction band and the valence bands, the electron affinities from the vacuum level, the band gap of the semiconductor, and the relative permittivity of the semiconductor of the user's choice. So it's time to have a look at our very simple Excel graphical calculator. So we will go to our Excel sheet and run some simulations. All right, so we are at the Excel calculator, and we would try to understand the parts of the Excel calculator before changing anything here. So this part that you see on the screen is regarding the left side of the junction. In this particular case, you can see from the green highlighted box that it is an n-type with a doping concentration of 1 exponential 15 per centimeter cube. And then here you see the right-hand side of the junction and its parameters. You can see that in this case, it's a p-type doping with 1 exponential 15 per centimeter cube doping concentration. The yellow highlighted boxes on both sides represent electron affinities, band gaps, intrinsic concentration of carriers, and the density of states in the conduction band and the valence bands. In case of p-n junction, this should remain the same for both the sides. And then the pink highlighted boxes are calculated from the inputs in the yellow and the green boxes from the user. And these represent N naught and P naught on the left side and the right side respectively, E sub C minus E sub F, E sub F minus E sub V, and the levels of the conduction band, valence band, and the Fermi level with respect to the vacuum. And then we have the basic junction parameters. So these show up once the junction forms, which is the V naught, the delta E sub F that we have discussed in the presentation, the E sub F for the homojunction that's formed. So that's the pinning of the Fermi level after the junction is formed. The E sub C of the homojunction or the p-n junction, and the E sub V of the p-n junction. Then we have the E naught and E sub R. We have the constant Q. And from all the above values that are calculated, we can then calculate the width of the depletion region, which we have converted to micrometer here, and then calculated the width of the depletion region on the left side and the width of the depletion region on the N side, or the left side and the right side. Okay, so let us go back up, and in this case, the left side is N-type and the right side is P-type, and we have this band diagram of the p-n junction that you see on your screen. And there are two colors that have been used in this. One is what we will call green, and the other is orange. So the green colors represent the valence band, the Fermi levels, and the conduction band. So these are the dark green, E sub V, light green, E sub C, and the green dashed line is E sub F. So for the left-hand side, it's N-type. So the E sub F is closer to E sub V, and the right side is P-type. So E sub F is closer to the valence band. So the green lines show the N-type and the P-type, or the left side and the right side, before the formation of the junction. The orange lines show the p-n junction, which is the energy band levels after the junction is formed. So the first thing that's very important is that the orange dashed line is where the Fermi level will pin itself under equilibrium. And this essentially is the average of the Fermi levels before the junction is formed. Then we need to ensure that the conduction band of the left-hand side, in this case the N-type, maintains the same EC minus EF that was there before the junction formed. On the right side, in this case the P side, we need to mention that we need to maintain that the EF minus EV after the p-n junction formation remains the same as EF minus EV before the junction formation. And then we are going to go through a series of calculations that are in the back-end sheet that help us form this shape. And we know that this shape essentially comes from the charge density, the electric field, and the potential that eventually causes the shape of the band diagram that you see, in this case the orange colors. Okay, so now we are going to go to the back end sheet. But before we go, we just want to see this value of the width of the depletion region on the left side. So it's minus 0.61. So we're going to remember that, minus 0.61. Okay. So we are at the back end sheet now. And in the back end sheet, we have the value of x. We have the charge density, the electric field, the potential, the conduction band for the p-n junction, the valence band for the p-n junction, the levels of conduction band, valence band, and Fermi levels before the junction formation, and the Fermi level where the p-n junction Fermi energy is pinned. So we start our x value at the width of the depletion region on the left side, minus 5. So we have minus 5 microns. So what we can do is to see the bulk energy levels before the change happens. And the graph runs from the width of the depletion region on the left side, minus 5, to the width of the depletion region on the right side, plus 5. So this enables us to see the energy levels in the bulk and at the junction. So this is the formula that has been used for the charge density. You can see it here. And essentially, it means that for the value of the width of the depletion region, for the value of x that is greater than the width of the depletion region on the left side up until 0, and if the left-hand side is an n-type, the charge density will be q times n sub d. And if it is p-type, then the charge density should be minus q n sub a. Then for values of x that are between 0 to the width of the depletion region on the right-hand side, and if the right-hand side is p-type, give the value of minus q times n sub a, and if it's n-type, give q n sub d. Else, if for all other values, the charge density is 0. For the electric field, we have used the similar conditions as for the charge density, except that we have used the formula for electric field. And in addition, at x equals 0, we have said that the graph should continue to follow the left-hand side. Whether it is n-type or p-type, it should just continue to follow the electric field formula for the left-hand side. And that's because at x equal to 0, doing so will help us achieve the maximum electric field which occurs at x equals to 0. And for all other values, the electric field will be 0, except from the width of the depletion region on the left-hand side, right up to the width of the depletion region on the right-hand side. And then we start the potential at 0. because that's what we would expect it to be in the bulk. And then we simply use a trapezoid integral of the electric field to get the potential rise or potential drop, depending on whether the left-hand side is p-type or n-type. And from here on, it is simply a matter of first pinning the Fermi level of the heterojunction at an average level of the Fermi level on the left-hand side and the Fermi level on the right-hand side. And then to calculate E sub c of the PN junction such that the EC minus EF of the left-hand side continues to remain the same as EC minus EF of the PN junction. And in addition to that, we will add the values of the potential to E sub c to give the final value of the E sub c of the PN junction. And then E sub v of the PN junction is simply E sub c minus the band gap. So these values pretty much run from the first row of Excel right up to the 500,000th row of Excel. And the reason why so many rows are involved is because depending on the doping that the user inputs, the width of the depletion region on one side could be much larger than the width of the depletion region on the other side, and so we need to cater to that. Given also that the value of x increments with 0.001. So assuming that one side has close to intrinsic concentration and the other side has close to levels of mobile carriers or electrons, as in case of the sea of electron cloud, so 1 exponential 20 or 1 exponential 22, given the increment of 0.01, we could do some calculations to figure out that we would at least need 500,000 rows in order to be able to start at a value of the width of the depletion region on the left side minus 5, and giving enough points, xx points, so that we can cross over the junction and go up to the width of the depletion region on the right hand side plus 5 microns. And in order to ensure that this dynamic nature of the graph is maintained based on the input from the user, we have used offset function to plot the graph of the energy band diagram, of the charge density, of the electric field, and of the potential. Okay, so now let's have some fun with the graphical calculator. We would go to the front end again, and let us see what happens if we change this to p-type, and this to n-type. And there we see the band diagrams now. First, let's look at the green one, where the EF on the left side is closer to the EV, and the EF on the right side is closer to EC. So this is p-type and this is n-type. In this case, the charge density signs would have been reversed, and so the electric field is now negative, and so the potential is dropping, and that's what we see in the band diagram as well, where at the junction the energy levels are gradually dropping. Now, let us say if we reduce the doping concentration on the left-hand side by an order of magnitude, you would see the graphs change, and you would see that the width of the depletion region on the left side would now be more than the width of the depletion region on the right-hand side. And this is something that would be confirmed in the plots of the charge density, the electric field, and the potential. And what happens if we increase the doping concentration on the left-hand side by an order of magnitude compared to 1 exponential 15? So as we would expect, this would be opposite. The energy levels are going to drop in such a way that the P side width of the depletion region is much less than the width of the depletion region on the N side, or in this case, the right-hand side. And this is also verified by the plots of the charge density, the electric field, and the potential. So in essence, you can play with this calculator by changing the n-type or the p-type on the left side or the right side, and using various doping concentrations. So we'll do one more. And this time, let's reduce the doping concentration of the left-hand side by an order of magnitude 2 compared to 1 exponential 15. So we'd go down to 1 exponential 13. And you can see that we take some time before the graph actually shows up, and that's because you can see these calculations that are going on. Remember that we have about 500,000 rows, so these calculations take some time before the values change, and you can see the change in the graph then. So now obviously the width of the depletion region on the left hand side is much more than the width of the depletion region on the right hand side. And you can see the same coming up in the graphs of the charge density, the electric field, and the potential. And what happens if we change this, the left-hand side to N-type, keep the same doping concentration, and change the right-hand side to P-type with the same doping concentration. And once again, you can see the Excel is starting to do the calculations right now. Right here on the screen, it takes some time. And then once it's done, you'll see the change take place in the graphs. There we go. And the same being reflected in the graphs of the charge density, electric field, and the potential. Now, one of the things that we should caution is that given that our increments of x-axis is in 0.01, if the width of the depletion region becomes less than 0.01, then we would miss points for the calculations of charge density on the left side or the right side, depending on which side is less than 0.01 micron, given the doping concentration that the user might put. And so those points would miss out in the electric field and the potential, causing possibly errors in the final outcome of the band diagram. But as long as the width of the depletion region is greater than 0.01, the graph gives a good appreciable shape of the band structure. So we are back to the slides from the Excel calculator, and we have learned some lessons. One is that the material characteristics remain the same for both the P side and the N side because it's the same semiconductor. The built-in voltage, which is the delta E sub F, the difference between the Fermi levels on the P side and the N side, is given by KT divided by Q, natural log of N sub A, N sub D, divided by the square of the intrinsic carrier concentration. And the width of the depletion region at equilibrium, because of the built-in potential V naught, is given by the expression of W naught. And this is doping dependent. So you see within the expression N sub A and N sub D. And obviously you see V naught. But it's also material dependent because you see the permittivity of the semiconductor within that expression. And finally, the Excel sheet does not take into consideration any bias voltage, forward bias or reverse bias being applied to the PN junction. So the Excel graphical calculator considers simply the equilibrium conditions. Now we move to heterojunctions. And we know that from the Excel calculator that at the junction we would have fixed ions that form charges and a charge density. there's an electric field, there's a potential that's caused because of the electric field, and so the energy band diagram of the p-n junction forms. But in case of a heterojunction, we can quickly see from the figure on this slide that there could be three scenarios. The first type is the straddled or nested heterojunction, in which the energy bands of the narrow band gap material lies within the energy bands of the wider band gap material. The second type is called the staggered heterojunction, in which the conduction and valence bands of one material is either above or below the corresponding conduction and valence bands of the second material. And the third type is the broken heterojunction, in which the conduction bands and the valence bands, or the entire band structure of one material is either above or below the entire band structure of the second material. So looking at this figure, we can quickly conclude that while V naught continues to remain delta E sub F, which is the difference in the Fermi levels of one material and the second material, but it is not equal to kT over Q natural log of N sub A N sub D divided by the square of the intrinsic carrier concentration, because the intrinsic carrier concentration would be different on each side. We can also quickly conclude that the W naught expression of the p-n junction is no longer valid because the materials are different. We also can conclude that the electron affinities on either side are different. Also, the band gap of one material is not equal to the band gap of the second material. So the band gap on the left side is not equal to the band gap on the right side. And therefore, there is a delta E sub G. Same with the conduction bands and the valence bands. The conduction band and the valence bands on the left side are not at the same levels as that of the right-hand side, causing delta E sub C and delta E sub V. So what would be the expression for the built-in potential and the width of the junction for a heterojunction? Well, we can start off at the basics, where V naught is equal to the change in the Fermi level energies of each of the materials, and therefore is equal to the work function of the P side minus the work function of the N side. And this is valid for all the three types of the heterojunctions shown in the figure on this slide. We plug in the values for the work function of the P side and the work function of the N side and get the second expression on this slide. And finally, we get the third expression on this slide. The green colored part of this expression is very similar to the p-n junction. The blue part comes from the differences in the electron affinities of the two materials, and hence the difference in their respective conduction band energies. The orange term takes care of the difference in the band gaps of the two materials, and the gold term takes care of the differences in the density of states in the conduction and the valence bands of the two different materials. Now, note that one could argue that V naught is the work function on the N side minus the work function on the P side. And that's a valid argument. Now, once if you try to do that, then the signs of delta E is going to change. And so based on the reference given on the slide, we have concluded that the signs of delta E should be taken with a grain of salt. So cum grano salis. The expression for the width of the junction W naught is also given on the slide, and the expressions for the widths of the junction on the P side and the widths of the junction on the N side is also given on the slide. What is important to note here is that the permittivity of the two different materials have been taken into consideration in the formula. The formula also includes doping concentrations of the two different materials alongside their respective permittivities. In addition to the difference in the formula for V naught and W naught for heterojunctions, we have to consider further complexities when dealing with heterojunctions. The first such complexity is doping. So we could have a PN heterojunction, we could have an NP heterojunction, but you could also have an NN heterojunction or a PP heterojunction. And it is quite possible that the doping on one side of the material or one of the materials is much higher than the doping in the other material. Further, what about intrinsic materials? And if intrinsic materials are combined to form a junction, we would have to take into consideration the band gap. So the flow of the carriers between the wide and the narrow band gaps need to be taken into consideration. And all this that we have talked about so far with regard to doping is to try to figure out where the Fermi level is going to pin itself in case of the heterojunction. The second consideration is material. So usually when we talk about junctions, we might assume that we are talking about an inorganic material forming a junction with another inorganic material. But it could be an inorganic material forming a junction with an organic material. And what are the complexities that we need to take into consideration when that happens? We are going to see that in the coming slides. And the materials could be both two different organic materials. The third consideration is alloying. And we do know that alloying could change the band gap of the material that is being alloyed. In case of heterojunctions, this could possibly change even the type of the heterojunction. So we are trying to analyze the figure given on this slide that's taken from the reference given below on the slide as well. And you can see that when magnesium is added to zinc oxide, the band gap increases by 1 electron volt, and it is entirely the conduction band that moves up. Now, if the conduction band moves up by 1 electron volt, it means that the zinc oxide heterojunction with 6p has moved from type 2 to a zinc magnesium oxide heterojunction with 6p, which is a type 1 heterojunction. And this means that a type 2 material that enables the dissociation of excitons into electrons and holes for solar cell applications could be changed by simply alloying the material and forming a type 1 heterojunction. The same materials could now be used in a LED or light emitting diode application. So the electrons and holes could flow into the narrow band gap material and recombine radiatively. The fourth consideration is the crystal orientation during growth. As you could see in the figure taken from the paper in the reference, the delta EC in figure A is different from the delta EC in figure B. The delta EVs are different, and even the work function from the vacuum levels are different. And all this is simply because the zinc oxide was grown in a different crystal orientation, um, which in turn affected the orientation in which the 6p was deposited on the zinc oxide. So the crystal orientation during growth plays a crucial role in the heterojunction characteristics. Another consideration would be the interactive nature of interfaces seen in a case of inorganic and organic heterojunctions. The figures on this slide are taken from the paper in the reference. And on the left side, you see the individual band diagrams for indium phosphide, alpha NPD, and copper phthalocyanine. Analyzing this, we could conclude that both the organic materials would form a type 2 heterojunction with indium phosphide. In case of indium phosphide and copper phthalocyanine heterojunction, we do get a type 2 heterojunction, but it is not as what we would have expected because the delta EV is much smaller. And in case of indium phosphide and alpha NPD heterojunction, we get a completely unexpected type 1 heterojunction, where the valence band or HOMO of alpha NDP has fallen below the valence band of indium phosphide. And so the reason why this happens is because there has been an interaction between the inorganic and the organic compound at the interface. So the reaction that happens between the inorganic and the organic compound just at the interface needs to be taken into consideration when we are dealing with the kind of heterojunction that may be formed between inorganic and organic materials. In practice, the band diagram, the band energy diagram for the heterojunction is measured via experiments. The most common experiments are photoemission spectroscopy and optical absorption spectra to figure out the values and parameters that would show how the bands line up at the junction. And obviously these values help in forming a more accurate shape of the heterojunction. In fact, the experimental methods of figuring out the band diagram for heterojunctions are by far considered the most accurate method for measuring the band diagrams for a heterojunction. In addition to the experiment methods, there are several numerical calculation methods of figuring out the band diagram for a heterojunction. The accuracy of all these calculation methods, numerical methods, are debatable, but people are fairly content with the shape that comes out through these methods. One of these methods is the electron affinity rule introduced by Anderson in 1962, which essentially states that the difference in the conduction bands of the two materials is conserved in the heterojunction. And the same is true for the difference in the valence bands. Another method is based on the bulk band structure introduced by Frensley and Kromer in 1976, which makes use of three different pseudopotentials uh, found in the bulk of a semiconductor to predict the discontinuities at the heterojunction. Another method introduced by Kromer et al. In 1980 was to make use of a numeric capacitance voltage profiling for the heterojunction to measure the band structure. And additionally, we have the density functional theory DFT calculations that could help form the structure of the heterojunction. Once again, it is important to note that in the science community, the accuracy of these numerical calculations is debatable. But people and the science community is fairly content with the shape of the band diagram that comes out as a result of these numeric calculations. So if we want to proceed to make a simple Excel model of the band diagram for a heterojunction, we would have to consider certain inputs to empower the user. These include the ones that we saw for the simple PN junction. To choose the left side and the right side as either N-type or P-type, the doping concentrations, N sub A and N sub D, and the specific material characteristics. In addition, we would have to consider doping. So the left side and the right side could be the same type, such as both of them could be N-type or P-type, just varying doping concentrations, or even intrinsic. Material characteristics such as the intrinsic concentration, the density of states, electron affinities, band gaps, and relative permittivities are going to be different for the two different materials. And the materials could be both inorganic or both organic, and could be a combination of inorganic and organic. We would have to consider the effects of alloying, crystal orientation during growth, and the interactive nature of interfaces, particularly in inorganic and organic heterojunctions that we discussed in this presentation. Okay, so we have seen the importance of the junction, its formation, its content, which is the charge, electric field, potential, and this leads to the energy band diagrams. We saw the PN junction, which is fairly straightforward, but when we want to build a simple Excel model, we have to make some careful considerations. The heterojunction is complex, and it requires further considerations in building a model. There are several calculating and prediction models, but their accuracy is debatable. And the models help in forecasting the shape, but it is the experiments that help in attaching accuracy to that shape. There are several models that require downloads and installs or use of specific software techniques such as DFT. However, the simple Excel model is easy to use but it allows for a basic shape of the band diagram only. So the next steps would include characterizing the simple heterojunction model using Excel simply because of its simplicity and accessibility, and to make the required considerations as was discussed in this presentation. Then the idea is to compare the Excel model with other complex models to check for conformity with the shape of the heterojunction band diagram that we get. And further, to perform experiments on the materials that we use to build the heterojunction in practice, and measure such characteristics once again to confirm or to check the conformity with the shape of the heterojunction band diagram that we would get from Excel. Thank you to Dr. Adrian Kitai, my professor and supervisor, for his continuous feedback, encouragement, guidance, and mentorship towards heterojunctions. And thank you to Sam Peter for his continuous constructive feedback that helps me continue and progress with the Excel model. And thank you for listening to my presentation. There are a number of backup slides that are going to follow this video. These backup slides include the formula that has been used in the simple Excel graphical calculator, along with the meaning of those formula. Thank you very much. Stay safe, stay healthy. Thank you.